విద్యా విధానంలో డాక్టర్ బిఆర్ అంబేద్కర్ ఓపెన్ యూనివర్సిటీ దేశంలోనే మొట్టమొదటి సార్వత్రిక విశ్వవిద్యాలయం. దాదాపు 2.5 దశాబ్దాలుగా దూర విద్యా విధానం ద్వారా కంప్యూటర్ కోర్సును అనుసంధానం చేస్తూ BA, BCom, BSc డిగ్రీ కోర్సులను అందిస్తోంది. పోస్ట్ గ్రాడ్యుయేషన్ స్థాయి, డిగ్రీ, డిప్లొమా స్థాయి కోర్సులను ఔత్సాహికులైన విద్యార్థులకు అందిస్తోంది. డెవలప్మెంట్ స్టడీస్లో సెంటర్ ఫర్ ఎకనామిక్స్ అండ్ సోషల్ స్టడీస్ ద్వారా MPhil, PhDతో పాటు విశ్వవిద్యాలయమే స్వయంగా దూర విద్యా విధాన అంశంపైన PhD వంటి పరిశోధనా కోర్సులు ప్రవేశపెట్టింది. రాష్ట్ర వ్యాప్తంగా సుమారు 4.5 లక్షల మంది విద్యార్థులు ఈ విశ్వవిద్యాలయం నుంచి ఉన్నత విద్యావకాశాలు పొందుతున్నారు. డాక్టర్ బిఆర్ అంబేద్కర్ సార్వత్రిక విశ్వవిద్యాలయం స్థానికంగా స్వయం బోధనా పద్ధతిలో ముద్రణ రూపంలో రూపొందించిన కోర్స్ మెటీరియల్ అందిస్తోంది. కోర్స్ మెటీరియల్ అధ్యయనానికి సహకరించే విధంగా రేడియో, టెలివిజన్ పాఠ్యాంశాల ఆధారంగా కార్యక్రమాలు ప్రసారం చేస్తోంది. అధ్యయన కేంద్రాల ద్వారా ఏర్పాటు చేసే సలహా సంసర్గ తరగతులు, సైన్స్ ప్రాక్టికల్ సౌకర్యాలు విద్యార్థులకు స్వయం అధ్యయనానికి ఒక చక్కటి అవకాశం. ఇవి విద్యార్థి సమీపంలో ఉండే అధ్యయన కేంద్రం నుంచే పొందొచ్చు.
Hello, good afternoon to the viewers of the Dr. B.R. Ambedkar Open University PG Teleconference program. Today's topic for the teleconference program is concept of aromaticity in benzenoid and non-benzenoid aromatic hydrocarbons. This topic is in the PG first year of our Dr. B.R. Ambedkar Open University. So in this topic, the speakers are going to enlighten you with the concept of aromaticity, criteria of aromaticity, then regarding the Frost-Muslin diagram, then alternate and non-alternate double bonding system, then annulenes, then non-benzenoid aromatic hydrocarbons, then stability, then limitations of Huckel's role, etc. So here, before going to the topic, just I would like to give a few lines regarding the concept of aromaticity. You all know that you have studied in your undergraduate classes regarding the aromatic compounds and aliphatic compounds. Organic compounds are classified into two things. One is aliphatic hydrocarbons, other is aromatic hydrocarbons. Now, difference between these two is aliphatic hydrocarbons are fat-like compounds. For example, all our alkenes, alkanes, alkynes, all these things will come under aliphatic hydrocarbons. Now the next thing is aromatic hydrocarbons. Now here in the case of aromatic hydrocarbons, the first compound was found out by a scientist by name Michael Faraday. He is a British scientist. He found out from the illuminating cylinders of a natural oil, that is whale oil. So he called it as a benzene. Now afterwards, another scientist, German scientist, Mitscherlich, he synthesized. Faraday found out naturally, but Mitscherlich synthesized this benzene by the action of calcium oxide on benzoic acid, and he got benzene. And Mitscherlich is the first scientist who has given the molecular formula and molecular weight of this particular benzene. So later, so many benzene derivatives were identified, you all know. And what is the difference between these aliphatic hydrocarbons and aromatic hydrocarbons? Now if you see that aroma means fragrance, Now all these aromatic hydrocarbons were generally prepared or extracted from balsams, essential oils, resins. So for that reason aroma name was given. Whereas these aromatic compounds have distinct from aliphatic hydrocarbons. But now the term aroma with fragrance is outdated, because now aromacity is concerned with not with the fragrance, but with the chemical reactions. That means now aromacity is more confined to the chemical connotation. For example, in the case of benzene and its compounds, these aromatic compounds are showing substitution reaction instead of addition reactions. They do not undergo oxidation reactions. They do not decolorize bromine in carbon tetrachloride. They do not decolorize aqueous potassium permanganate solution. So all these things will tell us regarding the aromaticity. Now here, in the case of aromatic compounds, there are first two compounds, that is before 1965, only there are two compounds on which entire aromatic chemistry was dealt with. One is benzene and other one will be cyclooctatetraene. So a scientist by name Huckel, a great scientist, he has given a rule that is called as Huckel's rule, 4n plus 2 pi electrons, and he said that any compound which obeys this Huckel's rule is said to be an aromatic compound. Luckily, benzene obeys this Huckel's rule and it is an aromatic compound, but cyclooctatetraene do not obey Huckel's rule and it is not an aromatic compound. Later after 1965, and during 1965, a scientist by name Soldemir has done so many researches and he identified so many compounds like annulenes and other compounds, non-benzoyl aromatic carbons, and he has applied this Huckel's rule and found out whether a compound is aromatic or non-aromatic compound. So this is a brief introduction which you have, I think already you have quite acquainted in your undergraduate classes. Now here in the PG classes you have more regarding this aromaticity. Now in our studios we have two eminent lecturers to enlighten regarding this aromaticity and all its concepts. So I will introduce the first speaker, Sri C.H.Raghupathi Garu, who has got a lot of experience as senior teacher and is a counselor for undergraduate classes in our university, and other senior counselor is C.H.Koteshwar Garu, who is counselor of Dr. Ambedkar BR Open University for PG classes, and also he is a assistant professor in Silver Jubilee College, Habsiguda. So these two eminent lecturers will enlighten you regarding all the details of the aromaticity and all those things. And one more thing I wanted to tell you, this topic will delve up to 45 minutes. So if you have got any doubts on these topics, you can clarify your doubts by asking questions and by dialing to the phone numbers which were given by the studios. So please, all our listeners, please note down these phone numbers and you can make a call to these phone numbers. Please, all our listeners, please make a note of these phone numbers. The first phone number will be 040-270-31431 and the second phone number is 040-270-31432 and the third phone number is 040-270-31433. So I request the listeners and the viewers to confine your questions to the main our topic, that is concept of aromaticity in benzenoid and non-benzenoid aromatic compounds. Now I invite our senior counselor C.H.Raghupathi Garu to enlighten our students regarding the criteria for aromaticity. I request Raghupathi Garu to enlighten us regarding criteria for aromaticity.
First, let us see the significance of the term aromatic. During early stages of development of organic chemistry, a large number of organic compounds with pleasant smelling compounds are isolated from natural sources like resins, balsams, oil of cinnamon, oil of cloves, etc. So since these possesses some smell, generally based on that smell the compounds are aromatic generally sold. But these compounds are the behavior of these compounds completely differ from that of aliphatic compounds known at that time. So since they possessed pleasant odor, based on that one the compounds are referred as or termed as aromatic compounds. In Greek, aroma means fragrant smell. Later, the particular examination revealed that these compounds are related to benzene known at that time. And after some time, gradually, more number of compounds are invented or discovered, but many of them did not have any fragrant smell. So, as such, the significance of original term aromatic is lost. Then comes the question, what is aromatic or what is aromaticity? Here, since the benzene structure is known, related compounds are known, and based on that one, we have some idea about that. That is, the aromaticity is nothing to do with its order. Order is a physical property, but it is depending upon the structure. The chemical properties are determined such that it must be associated with that of the structure only. So, based on that one, all planar, conjugated, cyclic, delocalized pi electron containing compounds are said to be aromatic. The peculiar property or characteristic property exhibited by these compounds are called as aromatic character or aromaticity. Example, benzene, etc. Then comes, what is the criteria for the aromatic compounds? So, here the criteria for aromatic compounds is Huckel's rule. Based on molecular orbital calculations and quantum mechanics, a German scientist Huckel, he proposed one rule. It is called popularly Huckel's rule or 4n plus 2 pi electron rule. 4n plus 2 pi electron rule. Any planar cyclic structure obeys this rule, that is 4n plus 2 pi electron rule, are said to be aromatic. N is equal to 0, 1, 2, 3 onwards, this is an integer. Say for example, benzene. A benzene is most important and first member of aromatic series invented. Its aromaticity shown by this rule, that is 4n, n is equal to 1. 4 into 1 plus 2 is equal to 6 electrons. Since benzene contains 3 pi bonds, total 6 pi electrons, so that it is obeying this rule, it is aromatic in nature. So, such that all other compounds which are cyclic in nature, planar structures and conjugated pi system is there, then this is said to be aromatic in nature. This rule is supported by many examples like anilines, cyclic ions, heterocyclic compounds. Then these aromatic compounds are more stable. The reason for the stability is resonance energy. What is a resonance energy means? That is, it is calculated according to its heat of hydrogenation. Say for example, if you take cyclohexene contains one double bond. This on hydrogenation in presence of nickel, it gives more stable cyclohexane. Besides that, some energy or heat is evolved. This is called as heat of hydrogenation. It is for one double bond. Cyclohexene gives 120 kilojoules per mole. This is calculated one or experimental value. As such, benzene, Kekulé proposed benzene containing 3 double bonds. If 3 double bond containing benzene is subjected to hydrogenation, the same conditions in presence of nickel, 3 molecules of hydrogen are added and same cyclohexane is formed. The expected energy released is 360 kilojoules per mole. But actual benzene is hydrogenated. The heat of hydrogenation, besides formation of cyclohexane, the heat of hydrogenation for the benzene, it is only 208 kilojoules per mole you are getting. That indicating that cyclohexatriene or the Kekulé structure of benzene is 3 double bonds are there, but they are considered as localized bonds. But If this delocalization takes place, that is actual benzene, since delocalization, the energy of the system decreases and it possesses less energy, that is the difference is called as resonance energy. It is calculated like this, that is left side it is first here it is cyclohexene, it is subjected to hydrogenation. You are getting cyclohexane as well as 120 kilojoules per mole of energy. Then extreme here, that is Kekulé benzene structure, 3 molecules of hydrogen is consumed or added and we are getting cyclohexane, expected value is 360 kilojoules per mole, and in between we have actual benzene. A circle we are writing, that circle indicating that it is a delocalization of 6 pi electrons. Due to delocalization, it will become very stable. Thus, it possesses internally 152 kilojoules less energy. That energy is called as resonance energy of benzene. By that energy, it is more stable. It can be calculated like this. Resonance energy, it is expected heat of hydrogenation and minus the observed heat of hydrogenation. For example, for benzene, we have 360 kilojoules expected one, observed one 208, 152 difference we are getting. That 152 difference we are getting is nothing but that much less energy we have. At the bottom we are writing 2 Kekulé structures. Alternative double bonds are there. They are considered as localized bonds. That is why they are possessing localized bonds only. But when a real structure, these two are called as resonance structures of benzene or contributing structures of benzene. The actual structure is resonance hybrid or the delocalized hexagon, a regular one bottom, at the bottom we are writing here. So, this is containing 152 kilojoules per mole of resonance energy. By that energy, it is more stable. And coming to the important or peculiar or characteristic features of aromaticity. All aromatic compounds contain high resonance energy. Secondly, if you consider benzene for example, it is having 3 single bonds and 3 double bonds. The single bond length is 1.54 angstrom units, double bond length is 1.34 angstrom units. But if it is not localized bonds, delocalization takes place in benzene, all the 6 carbon-carbon bond lengths are 1.39 angstrom units you are getting. That indicating that it is a delocalized orbitals containing pi electron rich system. Then third point is, here all the carbons are sp2 carbons. sp2 carbons are linked with one hydrogen, that is sp2ch bonds are there. The bond stretching vibrations near about 3030 per centimeters you are getting, that is agreement with that of benzene. And fourth point is, generally we are having here double bonds are present in the structure. If you look like that is, it is considered as unsaturated compound. Unsaturated compounds generally undergo addition reactions. But here aromatic compound are due to aromaticity, instead of undergoing addition reactions, they preferred for the substitution reactions with retention of aromatic ring. These are the important or peculiar characteristics of aromaticity.
So, yes, now our sir, Raghupathi sir, has enlightened regarding the concept of aromaticity, discussing resonance energy, combustion data, heat of hydrogenation, Huckel's and all those things. So, with all these things we can say that benzene is perfectly a aromatic hydrocarbon, because Huckel's rule can be 100% can be applied to benzene. It is fully satisfies the benzene with aromaticity, and even aromaticity of benzene is also physically proved by proton NMR spectra. It is perfectly aromatic compound, no doubt about it. So, now we have our another eminent speaker, CH.Raghupathi. So, he will enlighten us, our students, regarding the alternative and non-alternative aromaticity. So, I request Koteshwar garu to enlighten our students regarding this topic.
Okay. Polynuclear hydrocarbons are divided into two types. One is alternate and another one is non-alternate hydrocarbons. If you taking one example, suppose benzene. Benzene is having 6 carbons, 3 double bonds. Each double bond center is called as 5 center. Each 5 center is marked with different symbols like alpha, beta alternatively. 2 adjacent centers are having different symbols are called as alternate polynuclear hydrocarbon. If those pi centers having same symbol, those hydrocarbons are called as non-alternate hydrocarbons. That is.
Oh, okay. Yes. So, now I think you might be knowing regarding the alternative and non-alternative double bonded systems. Now, I request Koteshwar garu to enlighten our students regarding the annulenes. Are they aromatic or are they non-aromatic, and what is their structure, and how this aromaticity and non-aromaticity for annulenes can be verified with Huckel's rule and all those things. I request Koteshwar.
Yes. Before going to the annuline aromatic properties, first define the annulenes. What are the annulenes? Annulenes are the monocyclic conjugated polyene systems which are having general formula CnHn, where n is even number, because if n is odd number there is no existence of annuline. Therefore, always n is even number. Okay, that is annulenes. Then come to the aromaticity of annulenes. These annulenes aromatic property is explained by Huckel's rule. Okay. According to Huckel's rule, monocyclic conjugated planar hydrocarbons which are having 4n plus 2 electrons are showing aromatic property. But come to annulenes, these are represented by just one. Yes. These are represented by like this. Minimum lower membered annuline is 4n annuline. Next 6 annuline, 8 annuline, 10 annuline, and higher annulenes also exist. Then minimum number of annulenes, that is 4n annuline, 6 annulenes are aromatic planar rings. Therefore, those cyclic systems are having planar geometry are showing aromatic or anti-aromatic based on the electron number of electrons. Suppose annulenes are having 4n plus 2 electrons and planar ring system are showing aromatic property. Therefore, here benzene is 6n annuline, 6n annuline. It is having 4n plus 2 electrons. Therefore, it is having planar ring system and finally it shows aromatic property. But come to the higher membered 10n annulenes. 10n annulenes are having 10 carbons. These are irregular planar ring system. Therefore, it is non-planar ring systems. Therefore, it is not showing any aromatic properties, because even though it is having 4n plus 2 electrons, existence of different interactions, steric interactions or other interactions, it arranged in non-polar structure. Therefore, it shows non-aromatic or anti-aromatic property. Then finally, we conclude that annulenes which are having 4n plus 2 electrons and planar ring systems are aromatic. Then in the criteria of Huckel, the planar ring systems which are having annuline are shows aromatic properties up to 22 annulenes, and Huckel not explain above 24 annulenes. And non-planar annulenes, that is even though small membered annulenes or larger membered annulenes are anti-aromatic. Okay, this is about the annulenes.
Well, Koteshwar garu, you have excellently dealt regarding these annulenes, definition of annulenes and what are the annulenes, all those things to our students. Here, in the case of annulenes, So, for example, if we take anilines, so here also anilines are aromatic, and you said that there are some anilines which are non-aromatic. That means, so in this case, I think only benzene, which is a 6 aniline, is a benzenoid. Remaining other anilines are all non-benzenoid. So, in the case of anilines, only benzene is a benzenoid aniline, and except all other anilines are non-benzenoid anilines. So, that is a that means only one aniline is becoming a benzenoid, and all other anilines are non-benzenoid. And one more thing is here is, as you said, 10 aniline should be aromatic, but it is it should be, but it is actually non-aromatic.
Because of existence of structure.
Structure, yes. So actually, suppose if we apply Huckel's rule, so 10 anilines, it should be aromatic, but actually it is not an aromatic, as you said, due to various reasons like interactions, steric repulsions, hydrogen interactions. So this is not a actually. In fact, these 10 anilines will have 3 Kekulé structures, but all these 3 structures do not show aromaticity. Why? Because all these 3 structures are not planar. Yeah. So, and for example, if you take 14 aniline, so which must be according to Huckel's rule, which must be a aromatic compound, but 14 aniline is
due to its size, large member rings.
14 aniline, I think it is a aromatic compound.
Aromatic, but
because Huckel's rule, according to Huckel's rule, it is aromatic.
Aromatic.
Of course, some authors say it is not an aromatic compound, but even then, if we apply
according to Huckel's rule, it is aromatic.
It is aromatic compound.
But it is based on structure, geometry of structure.
Correct.
It is non-aromatic. Or anti-aromatic.
And similarly, for example, if you take another anilines like 18 anilone, according to Huckel's rule, it is a aromatic. But by, as you said, which structure is not aromatic.
According to generalized rule, Huckel rule, 4n plus 2 electrons containing polycyclic, monocyclic or polycyclic conjugated polyene systems are showing aromatic property. This is theory. According to practical purpose or experimental purpose, these are all not showing aromatic property. It is due to its structural properties.
Interactions, steric repulsions, various things are there. So, very interesting this regarding aromatic aniline. So, I think only benzene, 6 aniline is a benzenoid, and remaining all are non-benzenoid. So, we can take them as a non-benzenoid aromatic.
Benzenoid and non-benzenoid classification is based on structure, because some of the structures are having at least one benzene ring. Those polycyclic hydrocarbons are called as benzenoid hydrocarbons. Or aromatic compounds. Some of the aromatic molecules without benzene ring are also showing aromatic property. Therefore, those are called as non-benzenoid structures.
So, this is regarding anilines. So, we have both benzenoid and non-benzenoid. Now, would you please enlighten our students regarding this very interesting concept of Frost-Muslin diagram or polygon circular system of arrangement?
Frost-Muslin diagrams are extension for the Huckel's rule, or also it is also called as support for the Huckel rules. Okay, it supports by the taking the molecular orbitals of Huckel. It is briefly explained the energy levels of molecular orbitals of hydrocarbons, conjugated polyene systems. In this concept, conjugated polyene systems are considered as polygons. These polygons are inserted into a circle. This circle is divided by equally with horizontal and vertical lines. Okay. The insertion is carried out in such a way that at least one carbon of polygon touches the bottom vertical line. Okay. This carbon center is called as lower energy bonding molecular orbital. Okay. Then remaining carbon centers are arranged in different places in the circle in equal manner. Okay. Then the molecular orbitals which exist below the horizontal line are known as bonding molecular orbitals, and the molecular orbitals above the horizontal line are known as anti-bonding molecular orbitals. Then some of the molecular orbitals collinear with the horizontal line. Therefore, these are called as non-bonding molecular orbitals. Okay. Then if you consider any one system, I am taking cyclobutadiene system. This cyclobutadiene system is having 2 double bonds and 4 pi electrons. Okay. these 4-5 electrons filled placed in circle in such a way that touches the bottom line of vertical point. Therefore, this is known as lower energy bonding molecular orbital. These molecular orbitals are known as non-bonded molecular orbitals. These are known as anti-bonding molecular orbitals. Okay. From the structure, cyclobutadiene is having 4 electrons. These 4 electrons filled in the molecular orbitals, these 4 molecular orbitals. In these molecular orbitals, filling is based on the Hund's rule and Pauli's rule. First, lower energy orbitals are filled by the electrons. Therefore, first it fills the least energy bonding molecular orbitals, and then non-bonded molecular orbitals, and then anti-bonding molecular orbitals. Here we have 4 electrons only filled in bonding molecular orbital first, and then here non-bonding molecular orbitals are having same energy. Therefore, electrons distributed equally. Therefore, it is called as not closed electron configuration. Therefore, it is anti-aromatic. Okay. By taking another example, this is cyclopentadienyl anion, which is having 6 electrons, and molecular orbitals are 5 molecular orbitals, which are arranged like this. That in this case, 3 bonding molecular orbitals, 2 anti-bonding molecular orbitals, 6 electrons filled in 3 bonding molecular orbitals. Therefore, fully filled, and no electrons in anti-bonding molecular orbitals. Then it is closed electron configuration. Therefore, the compounds which are having closed electronic configuration in Frost-Muslin diagrams are known as aromatic compounds. Another example, benzene, very familiar example. Benzene is also placed in circle according to Frost-Muslin rules. Then it is having 3 bonding molecular orbitals, 3 anti-bonding molecular orbitals, and in the benzene having 5 electrons in pz orbitals. That pz orbitals electrons filled in bonding molecular orbitals fully. Therefore, it is closed shell electronic configuration. Therefore, it satisfies the Huckel rule. Therefore, it is aromatic. And another example, larger membered ring, it is planar ring, tropylium ion or cycloheptatrienyl cation, in which it is 7 membered system, each having 1 electron, but in this case it lost 1 electron. Therefore, it attains positive charge. Therefore, it is called as cation. Then it is having 6 electrons. These 6 electrons filled in 3 bonding molecular orbitals, and it attains closed electronic configuration. Therefore, it is aromatic. Okay. This is about the Frost-Muslin diagram.
So, it's very interesting to hear Frost-Muslin diagram regarding the aromaticity and anti-aromatic. Now, we came to know that cyclobutadiene is anti-aromatic according to Frost-Muslin diagram, and benzene according to Frost-Muslin diagram is aromatic. And cyclopentadienyl anion, I think it is aromatic according to Frost-Muslin diagram, and cycloheptatrienyl cation is also aromatic according to Frost-Muslin diagram. So, with one diagram we can say which compound is aromatic and which compound is anti-aromatic.
Yes.
And Koteshwar garu, then can you just throw us, suppose with this Frost-Muslin diagram, so because we know that compounds are aromatic, anti-aromatic and non-aromatic, and are there any compounds which are non-aromatic? Can we say with Frost-Muslin diagram some of the examples which are non-aromatic? Instead of aromatic and anti-aromatic, yes, can we say some of the compounds are non-aromatic?
According to Frost-Muslin diagram methods, we can't predict the non-aromatic property.
Achha.
By using these diagrams, we predict aromatic property of the compounds or anti-aromatic property of the compounds. But some important rules, that is polygon, that means that must be planar. The molecule must be planar, which is inserted in the circle. If it is non-planar, it is not applicable for the Frost-Muslin method. Okay, that is one thing, and it is not explained by the conjugated polyene system which are having different CC bond lengths and different bond angles. Okay. This is the limitation of the Proust-Muslin diagrams. This is also similar limitations for the Huckel rule also.
Okay, so we have understood regarding this alternate, non-alternate, aromatic anions, Proust-Muslin diagram. Now we will come to the now we have discussed only regarding the benzenoid and all those things. Now there are certain other compounds in the ring which besides benzene some other atom will be there. So they also show aromaticity. So regarding that, I think you might have studied in your undergraduate classes in B.Sc, but here in M.Sc also the topic is there and some advanced concepts you are going to hear. So regarding this aromaticity, so I will request Raghupathi Rao garu to enlighten our students regarding the aromaticity of heterocyclic compounds and also aromaticity regarding the till now we have discussed only monocyclic. Now please enlighten us our students with aromaticity of polynuclear aromatic hydrocarbons. So I request Raghupathi Rao garu to enlighten us regarding these concepts. Aromaticity of heterocyclic compounds, then aromaticity of polynuclear aromatic hydrocarbons.
Heterocyclic compounds, since the term itself indicating that these compounds are cyclic in nature, hetero means different from the Greek. Almost all these are carbon compounds or organic compounds. In organic compounds, if it is cyclic, that is the organic cyclic compounds in which one or more other elements present besides carbon, these are called as heterocyclic compounds. Hetero in the sense that different or other than carbon. Carbon is a must, otherwise no carbon compound. So that is heterocyclic compounds has a definition that containing other element atom in the ring structure, these are called as heterocyclic compounds. There may be, depending upon number of carbons or number of total atoms present in that structure, we have 5-membered rings as well as 6-membered rings. For example, 5-membered rings containing 4 carbon atoms, 1 heteroatom like nitrogen, oxygen, sulfur. Nitrogen containing 5-membered ring is called as pyrrole. Oxygen containing 5-membered ring is called as furan, and sulfur containing heterocyclic 5-membered ring is called as thiophene. 6-membered containing, in that 5 carbon atoms are there, 1 nitrogen is there, it is pyridine, it is generally called. The importance of these heterocyclic compounds, most of the natural compounds are containing these heterocyclics. For example, pigments like hemoglobin, chlorophyll contains 5-membered heterocyclics of nitrogen. They are generally called as porphyrins. Here, these heterocyclic compounds are aromatic in nature. If you look into the molecules, these molecules in the top we are writing, first member is pyrrole, nitrogen 5-membered heterocyclic. Second one is oxygen containing, it is furan. Third is thiophene. Fourth one we are writing nitrogen containing 6-membered pyridine. If you see these 5-membered rings, for example, they look like dienes. For example, 1,3-butadiene. A diene is unsaturated compound. These should undergo the addition properties, but actually these compounds, instead of undergoing addition properties, they are undergoing substitution products with the retaining of the ring structure. How it is possible? In the sense that these are flat molecules or planar ring structures obeying Huckel's rule. Huckel's rule, already we know that it is 4n plus 2 pi electron containing any conjugated systems with planar rings. Here we see that all the carbons and nitrogen for pyrrole, for example, they are sp2 hybrid. sp2 hybrid orbitals they are using means they are planar in nature. So planar double bonds 2 are there, total only 4 electrons required according to Huckel's rule, there must be 6 electrons. Nitrogen contains lone pair of electrons. This lone pair of electrons of nitrogen is contributed towards the ring system or towards the carbons such that aromatic sextet or 6 pi electrons are available. Since we are having 6 pi electrons more readily, that is nitrogen is giving or donating its pair of electrons, carbons are electron rich and somewhat nitrogen is electron deficient. That is indicated by its acidic character. It is nitrogen is linked with 2 carbons as well, 1 hydrogen. It looks like a diamine or secondary amine, but it is not undergoing any basic properties, it is undergoing acidic properties, that indicating that this is losing its electron or it is giving its electrons towards aromatic system. Like that furan also. Furan containing oxygen, it is having 2 lone pairs of electrons. Besides 2 double bonds, 1 lone pair of electrons from the oxygen is donated or contributed towards aromatic sextate, such that furan also aromatic in nature. Likewise, that is sulfur also. Oxygen and sulfur both present the same group. Like that, 1 pair of electrons are contributed towards that one. Since these are aromatic in nature, obeying Huckel's rule, indicated by resonance energy also. All these systems are 20 to 30 kilocalories per mole of resonance energy they are possessing. And if you compare to benzene, these are highly reactive towards electrophilic substitution reactions than benzene, that indicating that they are more aromatic in nature. That is indicated by, since it is heteroatom that is giving its pair of electrons, 5 atoms, total 6 electrons are there. Thus heterocyclic compounds also aromatic in nature. And these heterocyclic 5-member rings, for example, or 6-member rings, since we are confining to discussion for only 5-member and 6-member rings, heterocyclic compounds also we have fused rings also. But that is mostly available compounds in the natural products are these compounds, so that we are restricted to only discussion for these compounds. These heterocyclic compounds, particularly nitrogen heterocyclic compounds, are conveniently divided into 2 classes. One is pi electron rich heterocyclic compounds, another is pi deficient heterocyclic compounds. So example, furan if you take, in furan there are 4 electrons from the 4 carbon atoms, 1 lone pair of electrons constituted by nitrogen, such that total 6 electrons we are getting. Since nitrogen is giving its electron or share of electrons towards carbon, all the carbons in pyrrole are slightly more electron dense than the nitrogen, so that it is pi electron system or pi electron rich system we can say, so that it is undergoing very readily electrophilic substitution reactions than benzene, like aniline or phenol, it is more reactive. If you take pi electron deficient, for example, a 6-member ring you are taking, that is pyridine. Pyridine also containing a lone pair of electrons for the nitrogen, but already aromatic sextate was there in the ring, so that 3 double bonds are there, delocalized double bonds are there, planar ring structure. Since pair of electrons are not contributed towards that one, it instead it attracts electrons from the carbon atom towards itself, so that it is nitrogen becomes more electron rich than the carbon atoms, such that it is undergoing electrophilic substitution reaction rather slowly when you compare with that of benzene, because carbons are getting electron deficiency because of nitrogen is pulling electrons towards it, it is more electronegative, it is not contributing towards any aromatic sextate. So these are the 2. And besides these heterocyclic compounds, in hydrocarbons we have 1 ring containing hydrocarbons generally called as mononuclear. 1 benzene ring, for example, that is aromatic nucleus we say. Like that, if fused rings are there, more than 1 ring are there, these are called as polynuclear aromatic hydrocarbons. Originally, the Huckel rule only supposed to agree with that of monocyclic compounds only. Later, it is extended to polynuclear hydrocarbons also. For example, 2 rings containing, fused rings containing naphthalene, 3 rings containing anthracene, its angular isomer is phenanthrene. All these at the bottom we are writing this, that is polynuclear hydrocarbons, aromatic in nature. That is, first member is naphthalene, second member is anthracene, third member is phenanthrene. These are having alternate or conjugated double bonds, planar structures are there. These are obeying Huckel rule. How it is obeying Huckel rule means, first for example, the naphthalene. Here 4n plus 2 pi electrons, here n is equal to 2. Total in naphthalene we have 10 carbons contributing 10 electrons. So 10 electrons in the form of 5 double bonds we are taking, 5 double bonds. So total 10 electrons are there. If we verify Huckel's rule, 4n, n is equal to 2, 4 into 2, 8 plus 2 electrons, that is 10 pi electrons we are getting. It is obeying Huckel's rule, such that it is aromatic in nature. Likewise, anthracene. Anthracene we have 3, it is 14 carbons are there, contributing 14 electrons, 7 in the form of 7 pi bonds or 7 double bonds conjugated in nature. This is planar structure, such that it is aromatic in nature. How means it is agreeing Huckel's rule, n is equal to 3. 4 into 3, 12 plus 2 electrons, 14 electrons. It is agreement with that of Huckel's rule, so that it is aromatic in nature. Its angular isomer, phenanthrene also same, it is aromatic in nature. But one thing here, the aromatic character decreases from benzene to naphthalene to anthracene to this one. So even containing more than one nucleus, they are also agreeing or obeying Huckel's rule, they are aromatic in nature. And here the nature of the aromatic compounds, when you compare with that of mononuclear compounds, these are least reactive when compared with that of mononuclear compounds.
Well said, Raghupathi Garu, regarding this aromaticity of heterocyclic compounds and polynuclear aromatic hydrocarbons. So, sir has given a very lengthy discussion to our students regarding this aromaticity. Now, here just I would like to tell our students also. For example, if you take just now you have seen, sir told you regarding the pyridine. Pyridine exactly fits with the benzene system, and 5-membered heterocyclics, that is furan, thiophene and pyrrole. These 3 will be just like cyclopropenyl dienyl anion, because they will be having resemblance with the cyclopropenyl dienyl anion. So this is about aromaticity of heterocyclic compounds. And here one more thing I wanted to just to tell our students, there is one compound, one inorganic compound which obeys Huckel's rule. Very interestingly, it obeys Huckel's rule. For example, if you take this borozole, which is also called as borozine, B3N3H6. So the ring is a planar ring, and in the ring you do not have a carbon. It is an exception, because here in the ring only you have boron and nitrogen, and hydrogen atoms are attached to boron and nitrogen, but in the ring nowhere.
It is referred as a inorganic benzene.
It is referred as sir said, it is referred as inorganic benzene. It is inorganic benzene. So, but nowhere in this ring there are no carbon atoms, and it perfectly obeys 4n plus 2 pi Huckel's rule, but it is not an aromatic compound, because it is highly reactive compound. It undergoes addition reactions instead of substitution. It undergoes addition reactions. So it is a highly reactive compound. So it is not at all though it obeys Huckel's rule, this borozole, which is also called as inorganic benzene, it is not a aromatic compound. So this is about aromatic heterocyclic compound. Already sir told regarding the polycyclic aromatic hydrocarbons. Now we will come to the next topic. This will be enlightened by our D.Koteshwar Rao regarding the aromaticity of non-benzenoid aromatic hydrocarbons.
Yes.
So this is also a very interesting topic to our students. Till now we have discussed regarding the benzenoid. Now we will come to the non-benzenoid aromatic hydrocarbons.
Non-benzenoid aromatic compounds. Non-benzenoids are without benzene ring. Okay, those cyclic systems are called as non-benzenoid systems. Okay, several non-benzenoids are exist and shows aromatic property or anti-aromatic property. For example, I am taking cyclopentadienyl anion. It is having 6 electrons, that is 1 electron gaining from the outside. Therefore, it completes the 4n plus 2 5 electron rule of Huckel. Therefore, it completes the 6th test of aromatic property, and it is also planar. It is also planar, and it is having closed electron shell configuration. Therefore, it is aromatic and non-benzenoid. Non-benzenoid means without any benzene ring. And another system, azulines. Yes, azulene is this one. One of the 7-membered ring is fused with 5-membered ring. This one. Yes, this one. Okay. It is also having 10 pi electrons, that is n is equal to 2, therefore, it is 4n plus 2 electrons is equal to n 4 into 2, 8 plus 2, 10 electrons. Therefore, it is satisfy the Huckel rule, and it is also planar system, and it is also planar system. But one exception is it is not a monocyclic system, but we are extending the Huckel rule to the bicyclic fused ring systems. Therefore, it satisfies the all the conditions of Huckel, and but exception is bicyclic system, but it shows the aromatic properties, that means substitution reactions according to H1NMR criteria, all these criteria are satisfied. Therefore, it is aromatic. These are all non-benzenoid ring systems are showing aromatic property.
Yes. So now Koteshwar has explained to our students regarding the aromaticity of non-benzenoid aromatic compounds. So he has taken the examples cyclopentadienyl anion and azulene. I think there is one more compound, that is cycloheptatrienyl cation, which also comes under non-benzenoid aromatic hydrocarbon. So this is also a non-benzenoid aromatic hydrocarbon which shows aromaticity. So now here, suppose these are all, for example, if you take cyclopentadienyl anion or cycloheptatrienyl cation. So these are all ions. So we should not think that only neutral molecules will come under aromaticity. Even aromatic ions like cyclopentadienyl anion and cycloheptatrienyl cation, which are aromatic ions, they are showing aromaticity. Now here, if you see that, suppose if you take cyclopentratriene, which is a neutral molecule, which is non-aromatic. Cyclopentratriene is non-aromatic, and suppose by losing a proton, so it gets a electron pair and it becomes cyclopentadienyl anion, and it is becoming aromatic. Yes. So similarly,
where n is equal to 0,
yeah,
4n plus 2 electrons are 2 pi electrons. Therefore, it is aromatic
compound. Yes. Now here in the case of azulene just now Koteshwar has mentioned regarding azulene, which is a aromatic compound. So now here azulene we have got 2 rings, and it obeys Huckel's rule, 4n plus 2 pi electrons, which is coming under 10 electrons, which is having 10 electrons, 2 rings are there, and so 10 electrons are there. So now here in the case of azulene, there are 2 rings, one is 5-membered, other is 7-membered. So both contribute to this aromaticity, but here this azulene is also having a high resonance energy, which indicates that it is aromaticity. And here it was here in this case, in the case of 5-member, 7-member ring. So each ring, though one ring is having 2 and other ring is 3, but due to their mutual sharing, each ring will get a sextet of electrons. So that also we can say that.
You can take here cyclopropenyl cation also.
Yeah. Yes. So cyclopropenyl cation also comes under aromatic compounds. So all these non-benzenoid
that is
compounds.
Strong delocalization, sir. Strong delocalization of 5 electrons. Therefore, it shows the high resonance energy and therefore more aromatic.
Azulene is more aromatic, and because they are getting 2 rings are getting sextet electrons. So azulene is also a example for our aromaticity. So yeah. Fine. So now, in the end, because we are coming to the fag end of our discussion, so now I would request Raghupathi Rao garu to tell our students regarding the limitations of Huckel's rule. So what are the drawbacks and or limitations of Huckel's rule?
Like any other rule, here also Huckel's rule has some limitations. So here, first thing is, it is Huckel's rule applicable to only, that is a planar mononuclear polyanions containing up to 26 pi electrons. And secondly, it fails to explain why the rule is not applicable to higher anilines. And the third one is, though it is obeying are aromatic in nature, that polynuclear compounds. Already we mentioned that. That is, we have polynuclear compounds generally of naphthalene, anthracene, phenanthrene, like that. Even if you take the same isomers, anthracene and phenanthrene, anthracene is more aromatic in nature than phenanthrene. That is not explained because both are having 14 pi electrons. There are also 14 pi electrons. But how it is the difference between this aromaticity is not explained. Like that, anthracene, benzene is more aromatic in nature than naphthalene, then anthracene, then phenanthrene. Huckel's rule is unable to explain why this discrepancy. Now, these are the certain limitations for the Huckel rule, since no doubt majority of the compounds are agreeing this one, and wherever it popularly known as Huckel's rule is applicable to aromatic compounds, but certain limitations for every rule is there. Like that, these also certain limitations for the Huckel's rule.
So now regarding the Huckel's rule, Raghupathi Garu has explained. So we have covered almost all the topics coming under aromaticity. So then what are aromatic, what are anti-aromatic, what are non-aromatic, all these things were covered in this lecture, and the students, listeners have got any doubt, yeah, so they can ask regarding this one. So any doubts are there, they can ask the questions by dialing to the given phone numbers, so they can clarify their doubts by asking the questions to the speakers. So here, for example, there is then cyclobutadiene is also, for example, if you take cyclobutadiene, which is a anti-aromatic, which is an anti-aromatic, and the 1,3-butadiene,
Yes.
1,3-butadiene, which is also anti-aromatic, 1,3-butadiene. So here we can also explain regarding the pi electron delocalization also. For example, according to pi electron delocalization, 1,3-butadiene and cyclobutadiene. Similarly, 1,3,5-hexatriene and benzene. So like this, open chain compounds and cyclic compounds.
Yes.
So how do you correlate how do you correlate the resonance energy? Resonance energy, how do you correlate? Which one is more stable in terms of this resonance energy?
Yes.
For example, 135.
Yes, it established a diamagnetic ring current, sir, in the cyclic systems.
Yeah.
But in the case of a cyclic system, there is no diamagnetic ring current, but only existence of delocalization of pi electrons.
Yeah.
That is only delocalization. It creates some stability of conjugated diene systems compared with the saturated systems. But in the case of cyclic systems and acyclic conjugated polyene systems, in this case of cyclic systems, existence of diamagnetic ring current. This ring current enhances the aromatic property.
Okay, Koteshwar Garu, now I think we have almost time is over. So we have got a very interesting topic for our students, concept of aromaticity. Then I thank our eminent speakers, Raghupathi Garu, for coming to our studios and enlightening our students, Dr. Ambedkar University, and I also thank Koteshwar Garu for enlightening our students with his interesting lecture. Thank you very much to all our listeners. I once again thank all listeners for giving a patient hearing to all our lecture. Thank you very much. Thank you.